Hello everyone and welcome to this well test session. In this presentation we're going to have a look at a particular case study using Kappa Saphir, and this is an exploration and an appraisal well test for a vertical well in an oil reservoir, and this is deep water offshore. So what we see here is one of the gauge pressure and the rate versus time. So in Kappa we've got liquid rate, but if we go here on the document information, we've got only the oil. Okay, so the water phase could be neglected as the dominant phase is the oil phase. Okay, so we've got a cleanup with three distinct flow rate up to about 9.5 MBD, as you can see on the bottom right corner, and this is at maximum choke size. Then we choke back the well up to about 5.7 MBD, took the first PBU, which is quite a long one, so we got 10 hours here. It's about almost 40 hours. Then we got again a flow after flow test with three-step rate test, a long flow at about 8.5 MBD, slightly lower than this one, and a second PBU. Then we took some fluid samples at that time. So we've got a production of about 8.5 MBD, and for the drawdown we've got, so this is about 5,930 psi, and we've got about 55 psi, so roughly a drawdown of about 300 psi for producing at 8.5 MBD. So a rough productivity index of about 30 bars per day per psi, which is quite good for a vertical well, and we may be dealing with a high permeability reservoir. So this is exploration and appraisal well. So as per best practice, we should have multiple gauges along the tubing. So we can see the different gauges on QAQC tab here. Instead of having 12 gauges as sometimes standard in the operations, just for simplicity here we've got 3 gauges. Right, so the first thing we need to do is to QAQC the gauge, and we're going to do a gauge comparison. To do this, we can click on the icon called difference. So we can click on this extra DP and have a look at the log plot. So I'm selecting the reference gauge, or the deepest gauge, the one that we selected for the analysis. And now I can select my PBUs with this list, and or on this one I can click on the different PBUs, but I quite like this option, and I can just click on these two PBUs like this, and they're going to be highlighted in blue. You can see that the sampling is as well selected. We don't want this, so I'm going to remove that. I'm going to click on OK. Okay, so as we said before, we've got the long stabilization from 0.01 hour to about 10 hours. Okay, and now you can see maybe a slight increase in the derivative, and that could be due to the presence of some boundaries. Okay, so the next step now, we remove the tidal effects. We're going to investigate the convolution. So I'm going to click on the icon called the convolution. And as we mentioned in the well test session called the convolution, we've got 4 main methods. Let's extract a bit more, let's get a bit more data. Okay, now we are very confident. I'm going to click on OK. I've got my deconvolve response here. And I'm going to maximize this one. And again, we see, so what we see is the tail of the wellbore storage and skin, a long stabilization from 0.01 or 0.02 up to about 6 hours, and then an increase in the derivative. So this is probably indicative of radial flow regime. Okay, so we've done straight line analysis. So now it's time to select an interpretation model and to push the analysis further with a simulation. So again, on the model icon, our recommendation is to always start with the simplest well and reservoir model. Boundary model, we've got parallel faults. And so now we need to specify our parameters. So we got our first estimates of the well and reservoir parameters, which are the same here. Let's use this skin, then we can change that later on. Initial pressure, this is coming from the convolution. We use the convolution not only to get more insight into the reservoir, but also it helps us to refine the initial pressure. And it helps us to get a pure signal, free of any distortions. And then we've got our cage, which is 53,800. This is the same, so that's good. So for the estimate of these two boundaries, these are coming from the channel here. Okay, I didn't specify the fault, so it's assuming a symmetric channel. Maybe I can place... Yeah, that's not too great, but that's fine. So by doing this, I can pick the time of deviation due to the second boundary, which I did at, let's say, at this point. And on this one, I pick the deviation, the first deviation due to the closest boundary, or the first boundary. Here you go, and then I can click on generate. Right, so in the solid line, we've got a simulation. The delta P plot is not matched, but this is not a problem. This is the skin. Okay, so we're gonna leave it like this. Stabilization is matched. This is the cage. And now we can see that our simulation doesn't match the actual increase in the derivative. So we've got two methods here. Either we can improve the match using a manual process, just changing these values, or we can use the nonlinear regression and do an automatic match. So we're gonna do the two methods. And now I've got quite a good match here. So now what we need to do is to go back to our conventional analysis, use the conventional derivative as a verification tool, and use the other tools, superposition and the history plot, as verification tools as well. We need to make sure that this model match the other plots. And how are we going to do this? We're going to create a copy of this analysis too. And I'm going to extract the conventional response. So I'm going to use the final PBU just for simplicity. Here you go. So now I can see that the model that I extracted from using the convolution matched my conventional derivative and matched my delta P. It matched my superposition as well, and that's quite well. And it matched on the data plot, on the history plot. We have to make sure first that the PBUs are matched. Let's have a look at this. And it matched quite well the PBU. And please don't hesitate to zoom in, to assess the quality of your match. If you look at this, then you won't know too much. You need to zoom in and make sure that it matches your PBU. Okay, you've got gauges with resolution of 0.01 psi. You need to match your data. So now once we're happy with the PBU, we can have a look at the flowing periods. And this is going to give us some indication on the evolution of the skin over time. So we can see that the skin that I'm using on my model, which is 9.5, match this flowing period. But if we look at the rest, at the other flowing periods, now my simulated response is too high. I overestimate the pressure. Or if you like, let's say to produce at this rate, I underestimate the drawdown compared to reality. In reality, I need a higher drawdown than what I have in my model. So that means in reality, my skin at that point should be higher. This is a simple exercise, but this is to show you that probably we have some cleanup at that point as well. And that the skin that I'm using in my model is too small for the other flow periods. Okay, so that was one model.